All right, so here we go. So today's topic is binary search. But if there are any pressing questions about arrays, I can answer those. Yeah.
Or the last exercise for the section.
Number
I
10.
didn't quite get what you were asking.
Flatten.
Yeah.
So you've got 100 rows and 200 columns. So you imagine a table of 100 rows with a spreadsheet with 100 rows and 200 columns. And so you're going to take the first row and stick it in a vector. Then you're going to take the second row and attach it to the end of that vector. And you keep taking the next row and attaching it to the end of the vector. And you build up a vector that way. You're flattening out the two-dimensional array and putting it into a one-dimensional vector. Then you return that vector from the function. Do you want to see how to do it?
Yeah.
Oh, okay. Maybe that's what I should have done, is just show you how to do it. All right, that's it. All right, let's do flatten here. So what we've got an array of integers, which is 100 rows and 200 columns. And then we call this function flatten. Is that what it looks like? Yeah. And then we're done.
That's it?
Like I said, you don't need to write test code for this problem. I mean, you can. It's just very time consuming, and I don't want to do it now because I'm late today, and we want to do this other topic, and also it's not required for the problem. So we're going to skip the test code. So it looks essentially like that. Now this is an uninitialized array, so we're flattening basically random data. And so we have the function. It returns a vector of int. So a vector of int flatten, and it takes an array of int with 100 rows and 200 columns. And we return a vector. So it'll be something like, we'll create a vector v and then we return it. So we need to create the vector. The vector of int v and return v. So there's a stub right there. Oops. I get to do that.
We don't use any pushback?
Oh, we do, but not with the stub. Yeah. See, we just have a stub. We're not doing anything. I just want to see if it'll compile. All right. So now the vector v is empty. So we want to push the first row. So let's call it r. Start at row 0. And r row will be less than 100. So, if there's 100 rows, that means the row numbers are 0 to 99. Okay? So we never hit 100, so r is strictly less than 100. So what we're going to do is, we're at row r. First time we enter the loop, we're at 0, row 0. Second time we run the loop, we're at row 1. So in row r, what do? We have to push back all the elements in that row onto v. That means we have to iterate through all the elements in row r. So we'll use C for column. And there are 200 columns. And column numbering is the same as row numbering. It starts at 0. So C is less than 200. So for each column position in row R, for each column position C in row R, we need to push the value there onto V. So what do I write here? Who's following this? Who can read the code off to me? Huh?
But what I wrote is B dot pushback, and then parenthesis A, and then bracket I, and then bracket J.
Yeah, I'm going to translate that to R and C. That's exactly right. That's all you do. That's it right there. Problem's done. Not that tough. It's a nested loop. So you have to start thinking in terms of nested loops.
Yeah, I did the nested loop, and then I did the V dot pushback, and I just put them in separate, like pushback R, and then below that V dot pushback with parentheses C.
Yeah.
I put it too. I didn't do the array inside the vector pushback.
Yeah, you have to, the purpose of R and C are just indices into this table, this two-dimensional table. So we have to use this expression with the brackets to pull out the value at position RC. That's the expression that we use to access the value at position RC. Okay. All right, let's do this here. This won't be too bad. Binary search goes fast. And, let's look at this problem. You get a vector V and an integer K, and your job is to decide is K in V? V is a bunch of numbers, right? And K is some number. Let's say K is 7. So is 7 in V? We've got to look inside V to find 7, right? Let's suppose that V has 1,000,000 integers in it. So we look at the first one. So is the first one 7? No. All right. Is the second one 7? No. Is the third one 7? Yes. Oh, we found the number 7, K equals 7. We found 7 in the third position. So we'll return true. The value is in the vector V. But let's suppose that 7 doesn't appear in V. So we go through all the numbers checking, is 7 in position 99? Is 7 in position 100? Is 7 in position 101? All the way to the end of the vector. If the answer is no for every question, for every check, then we return false. K is not in V. I'm not sure I actually explained it there. I don't say what to return, right? So let me add that to there. But basically, it's not clear what I wrote there. There's a number of different ways to express the problem. The other way to express the problem, the other version of the problem is return the position of K in V. Don't tell me true or false whether K is in V or not. Return the position of K in V. So if I find 7 in position 3, I'll return 3. If I don't find 7 in this vector of 1,000,000 items, I'll return -1. Because that's not this problem, but that's the other version of the problem, is where you return the index of some value in the vector.
So this is going to be kind of similar to the counting occurrences exercise that we had in last lab?
Yeah, well, the way I'm explaining it now, it's similar. But now I'm going to change the situation a little bit. Now, what I've just been explaining is linear search, where you look at every single value. That's like count occurrences. You have to look at every value. But in this problem, we're assuming that the values in V are in ascending order. So they start small and they get big. They don't dip down. They're always staying the same or getting bigger. Now, you've got 1,000,000 items in V. You know, why? You don't want to use linear search. You don't want to start in item 1 and then go to item 2 like that. You don't want, that takes too long. What you want to do is like looking something up in an old-fashioned telephone book. You want to open it up in the middle and say, well, I'm looking for 7. Is it bigger than the value in the middle, or or smaller than the value in the middle? If 7 is smaller than the value that's in the middle of the vector, then I'm going to look at the first half of the vector, and I'll chop that in half. So you do what that's called binary search. We don't have to do that as much anymore. You know, we used to have things like dictionaries and telephone books. They're like disappearing. I'm from an old age. I'm gonna like die soon. You know, I'm like from the past. Has anyone in here looked up a word in a telephone book, a physical telephone book? How many people? Two sort of.
I mean, back in the
Maybe.
day, yeah.
Back in the day?
Yeah.
You remember that? Okay.
Yeah, we had this massive dictionary, massive telephone book. Yeah.
Yeah, you remember that, right?
We played
Okay.
we played
It wasn't
Scrabble.
too far off.
Oh, maybe your children won't ever look in those things. They may go into a museum and say, "What? That's a telephone book."
Daddy.
But anyway, that's how you actually look something up in an old-fashioned telephone book or dictionary. Now they do it in code, right? And that's why we're learning it here. So now you're learning how to code the algorithm that humans used to carry out manually. So we're not doing it anymore. We're designing robots to do it. All right. So let's go ahead and do this. Let me type that in there. So let's look at this. This is going to be, you know what, I'm going to give this to you in a different form, and you can put it in this form. Right. I'm going to show you how to do this with an array. This is the linear search problem here. This is where A is not in, you know, an ascending or descending order. It's just all mixed up. So you have to look at every value if you're looking for K in A. So I'll do this problem here, binary search, exercise 1, but I'll do it for arrays and not for vectors. So you'll have to do a little work there in lab. So the return value is a bool. True or false is K in A. So we have an array of integers A of length n, and we're looking for the value K. Remember, with arrays, you have to pass the number of values in the array. So that'll be the second argument here. And K, the value we're looking for, is the third argument. And then we return true or false. Let's just return true. So we have an integer A, which is an array, and it'll look like this: 3, 6, 9, 12, 21, 100, 101, just like that. There's just an array. And then we'll do this. We'll assert that binary search on A. What's the size of A? 3, 6, 7, yeah. So is 2 in there? This should return false. 2 is not in the array. But what about 3? 3 should return true. Oops. And so on. So we do our test cases here. So 3 returns true, and let's look at, say, 5, and 6, and 7, and 12 and 16, 21. Just making sure it works everywhere. 25 and 100, 101, and 1010. So this is false.
What about negative numbers?
Yeah, we can do that. Actually, let's do that right now. Let me get this first. This is 101 is true, 100 is true, 25 is false, 21, 16 is false, 12, 7, 6, 5. Am I doing that right? 7 is not in there, right? 6 is in there, 5 is not in there, 3 is in there, 2 is not in there. So let's make this minus. Let's use negative numbers. Let's use negative numbers and 0 too. So this will be, say we'll make this minus 22. Make this minus 3 is in there, and this would be minus 1 is not there, but 0 is there. That's it. That's a good suggestion to add the negative numbers. And then we've got a funny number there, 0, you know, so who knows what happens at 0. So let's put that in there. So basically we're checking each possible value that's in here. We want to make sure we hit each one, and we want to make sure that we get a good response for values in between all of these entries. So this should fail on the very first assertion. And what is going on? But we don't need vector, first of all, here. What was that? Up here? Oh, yeah, I didn't declare it correctly. I think you're right. It should look like that. Thank you. We're good. Very good. There it is. That was it. Look at that. So it's the first assertion, I'm sure. Line 13. We're looking for minus 22. So we're returning true. We need to return false there. Okay. So we got the test code set up. And let's do this algorithm. So it's like an old-fashioned telephone book. We need to go into this iterative process. We keep splitting the number of pages that we're concerned with in half. You know, first we split the phone book into two halves. We say, is it in the first half or is it in the second half? Or are we looking at it? Those three cases. Either we by chance, we open it up to the very telephone number we're looking for, or it's in the first half or the second half. So we're going to have a loop. And I'm just going to start with an infinite loop. Just going to rough it out like that, okay? So an infinite loop. And we're going to have some position that we're looking for. So it'll be something like if A of, well, I remember, it's going to be, we're going to calculate this midpoint. We're going to have a midpoint M, the index N. That's like the page number that the phone number is in. It's like the index in the array. So we're going to, M is going to be our midpoint. And we're going to start the midpoint in the very center of A, and then we're going to decide whether the midpoint goes to the left half of the array or the right half of the array, and so on. And we keep narrowing it down. So we have some kind of midpoint calculation. Well, that's pretty simple. The midpoint calculation looks like this. We're going to have a start value and an end value. And then we're going to divide by 2. We're going to take the average of 2 bookends. In the very beginning, start and end are going to be, at the extreme ends of the array. So S is going to be 0. The start value is 0. And the end value, or the end index rather, this is not the start value, this is the start index. It's the first value in the array. And the end will be the last value in the array, which is n minus 1. Now I just remember, we could try to use n, which is 1 past the end. But I remember that this happens to be an easier way to solve the problem. So that's my memory. And I used to not do this, actually. In this class, I used to use n all the time because I couldn't remember that. But now I know better. If I just use n, it makes the solution simpler. So I'm going by my memory here on that one. So S points to the first value in the array. E points to the last value in the array and in the outset. But then we're going to move S to the right, and we're going to move E to the left. We're going to squeeze in and hone in on K and find K. So the way we hone in is we take the average of the start and end points, and then we divide by 2, right? We take the average. In other words, we add S and E, we divide by 2. That gives us a midpoint. Now we may do some truncation there, because if this is an odd number, then we're going to lose, then there's not an exact middle index. But that's okay. We've got to pick one or the other. So we're like going down to the smaller index. So then after we get n, we want to say, well, did we find it? If A at m, if the value at m in A, if it equals K, we're done. We don't need to search anymore. We'll return true. We found K in A. And if we go through the loop and we never hit this, then we're going to say, oh, we didn't find K in A. There's other ways of solving the problem. We could put this inside the loop as well, but I'm not going to do that. Now let's suppose that A of m is not equal to K. So I'm going to do else if A of m you know what, I'm going to do it a little differently. I'm going to change this because this is not the way I think. I'm going to do it the way I think. If K is A of m, if K, the value we're looking for, if it's less than A of m, that means it's in the left side of this range. So it's between S and M, right? It may be at S, but it's not at M because we tried it at M, see? K is not at M. Now, the values in A, see down here, they're in increasing order. So if K is not equal to A of M, and, well, not and, but if K is less than A of M, then we know that K is to the left of M. So it must be inside the range S to M minus 1. So we're just going to set the endpoint to M minus 1. We're going to bring our end index in. When we don't set it to M, there's no need to set it to M because we know that K is not equal to the value at M. So we don't need to set it to M. So we'll set it to M minus 1. It might be, K might be at M minus 1. K might be at E. K might be at S as well. And let's suppose that K is greater than A of M. Then that means K is to the right of M. We're going to bring the start index up. So So we're going to adjust S is going to be, well, we know that K can't be at M, and it can't be, it has to come after M. The earliest it could come, it could appear is at M plus 1. Now what we got to do is figure out what goes there. Because S and E are squeezing together. And at some point, they're going to overlap. So at some point, let's think about it. It could be
All E is greater than S.
exactly. That's exactly what it is. While E is greater than S, is exactly what it is. Oh, wait a minute. I think it's also equal to, right?
Yeah.
I think we want to use that. Or another way to do it is, well, S is less than E, less than or equal to E. Because S is to the left and E is to the right, so I'm going to write it like that. So if S and E, let's suppose that S and E are getting squeezed together and they hit the same value. Let's suppose that S is 39 and E is 39. See, because M, we keep getting closer. Either we set E to this or S to that. E and S are going to either going to hit each other or S is going to get greater than E. Now let's analyze it. Let's suppose that S and E hit each other. So S and E are equal. So we're going to go into the loop. So we're going to take, let's suppose S and E are both at 39. There's going to be S plus E, that's 39 plus 39, divided by 2, that's 39, right? So M is 39. So M equals E and S. It's not a problem. And then we check it. Well, is K there? If we found it at 39, we'll return true. Otherwise, we'll check, well, is K less than A of M? And it can't be less than A of M. It can't be greater than A of M. I'm going to skip over that detail right now. And so, oh no, I'm sorry, it'll be one of the other. I'm sorry, it's one of the other. Hold on now. We're doing this without an example. I better use an example. Let's do it like this. Here's the vector, minus 22, minus 3. Let's suppose our vector looks like that, or the array rather. It's minus 22, minus 3. And S is here, and E is there. And let's suppose we're looking for K equaling minus 10. So K is in between minus 22 and minus 3. Right, minus 10 is bigger than minus 22, but less than minus 3. That's too confusing, right? Let's make it easier. I mean, we don't want to strain on this particular issue here. Let's get rid of the negatives. Once we're looking for 10, S is at the value 2, and the value that follows 2 is 30, and E is on 30. Let's see what happens. And we're going to calculate M. That's the average of S and E. S is 0, E is 1. So what do we get there? It's 1 divided by 2, that's 0. So M is set to 0. And because M is set to 0, we're going to compare, is S, which is 0, sorry, is K equal to A of M? In other words, is K, which is 10, is K equal to A of 0. Is 10 equal to a of 0? No, because a of 0 is 2. I know it's hard to keep track of this, right? You know, I can see that is, you know, is 10, sorry, m is 0. And we're looking for k, we're looking for 10. So the answer is no. We didn't find it because it's not in there. So we're never going to get equality. So this will never, in our example, this is never true because 10 is not in the vector. So that means we'll go to the next one. Well, is k less than a of m? Is 10 less than a of 0? Remember, 0 is, m is 0. And a of 0 is 2, right? So is 10 less than 2? No. So this is false. So is k, which is 10, greater than 2? Yes, that's true. And so we're going to take the start index and set it to 1 past m. So that s becomes e. Because remember, m was set here. M was at 0. And so 1 past m, the m plus 1 would be 1. So now s and e are overlapping. See, we didn't check the 30 yet, did we? So if k happened to be 30, then we need to check the condition where e and s are equal, because then we would find it. Because we're looking for 10. So we recalculate m. M is now 1 plus 1 divided by 2. And that equals 1. So m is 1, s is 1, e is 1. Remember, 1 is position 1 in the array, or the array. It's position 0. Now we check, is k equal to a of m? Well, no, because 10 doesn't equal 30. Is k less than a of m? Is 10 less than 30? Yes. Well, now we're going to modify e. So e will be set to m minus 1. So e is set to m, which is 1, minus 1. So e becomes 0. So look, the end is now smaller than s. So in the loop condition, the loop condition is now false. S is no longer less than or equal to e. S is now bigger than e. The loop condition is false. That means we squeezed so far, and we looked at everything we could. It's not there, we'll return false. Yeah, it's hard to explain this. I know there's better explanations of this on the web. You know, I know there's some YouTube videos out there that do a better job than I do. So you can look up a popular YouTube video on binary search. My students last quarter did that. I probably should have posted it. Skipped my lecture altogether. But even if you watch that better presentation of the algorithm, you're still not going to get it. You have to do it. You've got to spend a couple hours. Now, if you're a math major, maybe you don't want to do it, okay? But if you're a computer science major, a computer engineering major, you're going to want to spend some time and figure out binary search in your head and code it up and get it to work. You've got to do that as an exercise. It's what you need to do, because you'll have to figure out harder algorithms than this later on. If you don't practice with the simple ones in the beginning, you're not going to be able to handle the complicated ones later on. And we didn't check this. I think it's done. I think it's done. Oops. Let's take a look. How many people think this is going to run? How many people think it's going to say all tests passed?
Oh yeah, I have confidence.
You do?
Got it.
Anybody else? Anybody want to vote no? You're going to
So,
vote no?
we got
Good.
yes
You know,
and
I got to tell you, it's 50-50 here. Although I've done this so many times, I think I got it right. But I'm always, every quarter, I'm surprised when I get things wrong. Let's see. It compiles. Is it going to do it? Winner. All right. So, you know, you could do another test case. This is the case where you have an odd number of values in the array. We could try another one with an even number of values and see if we get the same result. Because there's some kind of difference when you have odd or even values. But that's it.
So in order to use a vector, we just still use the array. We just push back the array into the vector, right?
Yeah, you're going to use pushback. You'll push back -3, push back 0, like that. Yeah.
Okay. But we could just do the exact same thing, and then below that, just push back the array of A, right?
Yeah, and write a loop. You know, you'd have to write a loop to push each value of A onto V.
Okay.
It's very inconvenient, the vectors. This is very convenient initialization syntax for an array.
Yeah.
Unfortunately, it's not available for vectors. Now, I want to change this a little bit because you'll need, you have to produce this algorithm on the exam. I will guarantee you 100% probability I'm going to ask you a binary search problem. So you have to memorize the algorithm. I'm not going to ask you for test code. I'm going to ask you for this. You have to come up with that on the exam. And it's hard to derive it. You could derive it in your head during the exam if you're really smart. But you'll need to practice first. Yeah.
Is it the same for all binary search? The same algorithm?
Yeah. Well, you know, if it's descending, I might say, all right, it's not ascending. A is in descending order. Well, then now what do you do? Well, it's pretty straightforward there. You're gonna use you're gonna do something like that, right? So that works for now this works for arrays that are descending. You're gonna have to do that. Whoops. And I'm going to show you the other variations. There's a number of different variations. It's like a total of 8 different possible problems I can ask. Let's suppose I want you to tell me, I don't want to know whether K is in there or not. I want to know the position of K in A. So I'm going to return int. I want to know the index of K in A. Now, if you don't find K in A, then return -1. And this is standard. If you're looking for an index, if you call a function that finds an index of something, indices go from 0 to some positive value. So -1 is the largest invalid index. So if the function doesn't find that value, you return an index of -1. That's the standard, sort of a convention that's used. If you find it, then you want to return the index of where K is in the array. But a test code would look a little different. This would be -1. Wherever there's a false, it's a -1. And here, -3 is position 0. 0 is in position 1. 12 is in position 2. 21 is in position 3. Did I get that right? 0, 1, 2. I'm missing something there. Well, I never test for 9. That's all right. So this should be 12 is in, let's see, 0, 1.
3.
So that should be 3. I skipped 9. I didn't test for 9. Okay. This is 4, 5, and 6. And so now we're checking for indices. See, I know that being neat helps me think. And so I'm always trying to look for ways to be neat, make this code easy to look at. All right, so what goes there? We know that -1 goes here. We return -1 means we don't, before we were returning false, it means we didn't find K and A. Now instead of returning false, we're going to return -1, the invalid index -1. That's the convention for doing that. But let's suppose we do find it. Let's suppose we find K and M. What do we return? Good. Return M. M is the index that we're checking for the presence of K. Got it. That's the other basic form. To remember, ascending or descending, return an index, returning a bool, implemented with vectors or implemented with arrays. So it's 8 different possibilities. Yeah.
So why do we return -1 though if it's not true? Why -1?
What do you mean it's not true?
I'm sorry, if it's not at.
If it's not in the vector, if it's not in the array.
So what is -1?
So we have to return an integer. The function is declared as returning an integer. So we have to signal, I have to send a message to the calling code to let it know K's not in there. So how are you going to let the calling code know that K's not there? You send it an invalid index.
Okay, you can't have a position -1.
Yeah. So that's why in the calling code we check for that. Say, hey, did you return a -1? Oh, that means you didn't find -22 in the array.
Can you pick any invalid index? Like
You could do that, but you would be going against tradition.
Oh, okay.
Programmers will use -1 by convention because that's what we all somehow, it's not like we had a committee and agreed to the number. It's logical. Well, why would we use -3, say, or -2? -1 is the first invalid index. Let's just use that instead of some crazy number like -107 or something like that. But you could use another value. Or you could use an index that's past the end of the array. But that's not done in practice. What's done in practice is -1. Anything else? That's it for binary search. Well, let's look at what you need to do here. Finding the maximum value in a 2D array. And here's some more exercises on, this is not binary search, but it's part of this activity, this assignment. You need a nested loop to search through the array A, finding the biggest value. So we looked at a version of this already, I think for one-dimensional arrays? Yeah. So you just do it for a two-dimensional array now. So you have a nested loop. Linear search, I almost always have that on the exam. And this is really easy, linear search. And you can contrast that with the binary search. For small arrays, binary search and linear search are equivalent. But when you get very large arrays, then binary search is much faster. I can create an example for you where binary search will complete in less than a second, but linear search won't complete for the entire period that we have here. And you just have to hit the right, there's a certain threshold that you hit at. Because, you see, in binary search, the number of comparisons that you do is approximately equal to the logarithm, the base 2 log of the size of the vector. So if you've got 1,000,000 values to look at, you only have to, with binary search, you only have to look at, suppose you have 1,000,000 values in the vector. With binary search, you only have to look at log base 2 of 1,000,000. It's like, what value do you raise 2 to get 1,000,000? That's going to be pretty small, 10, right? Is that right, 10? The 10 is k, so it would be 20, 2 to the 20. So you do 20 iterations of the loop. If you have 1,000,000 values in the array, you only have to do your loop 20 times to know whether k is in there or not. But if the values are not in sorted order, you have to look at every single value in the worst case. That means your loop runs 1,000,000 times. That's a big difference. Running a loop 1,000,000 times or running a loop 20 times. That's a big difference, isn't it? And forget about 1,000,000. What about 10,000,000? You know, or 100,000,000. And if you take the log base 2 of 100,000,000, it's still going to get a small number. I mean, what, 30, maybe, something like that. I'm going to figure it out now, but I mean, still, even if it was 1,000 iterations of the loop, it's not a big deal. Then you're going to, you don't have enough space in memory to stress binary search. That's for sure. It doesn't, given the size of memory in these days, binary search will always run very fast. But linear search, I mean, wow. And suppose you have to copy, your whole memory. What's memory at these days? It used to be like 8 gigabytes. Is that what new systems are?
1 terabyte?
Yeah.
Huh?
1 terabyte?
A terabyte? Main RAM?
No, not
No,
RAM.
RAM is at 8
to 12.
8 to
for
12.
live
And
search.
now it's at 12, but when I bought my last computer, it was at 8.
24 in my computer,
You get 24?
in my home
Yeah.
computer.
Now imagine you got to copy 24 gigabytes, onto like a hard drive or something. That takes a long time, right?
Yeah.
That's like a linear search. Anyway, so finding the maximum value, that's like a linear search problem. Linear search. Here, I showed you this one. We did this one right here, exercise 4. Today we did this one. It's an array of int, and you're supposed to return the size, or the position of k in A. And this is, instead of using n, I use size here for the number of elements in A. And guess the number game. Now, why did I put guess the number game in here? So, like, you have some number. The secret number is 1023. And you have to create a user interface and guide the user so that ask them to guess the number. And when they type in a number, you read it and you say it's too big or it's too small. So what are we doing here? What if we have an intelligent user? The user will do what?
Keep on going.
Use binary search. In other words, this is an example of a computer, right, using a human to do its work for it. It's the other way around. So you got to watch out. In the future, computers will take over and control us. And this is an example of that right here. Okay. All right, that's it for today. Any questions? Up there.
Since we don't have class on Wednesday,
Oh, no class on Wednesday. That's right.
so what does that mean for lab? For people that have class?
Well, that lab will meet on Monday, so the labs are now different. Now the Monday lab people are now going to meet. Is that how it works?
No. Yes.
Let's all keep going.
And I'll tell you right now, not a lot of people are coming to lab. So you can come to any lab you want. Yeah. You can come to both of them if you want. Yeah.
Is it a due date for lab?
Well, it's right here, right?
So is
Oh,
binary
no,
search
it's
due
not.
Friday?
It's not changing. It's due. This binary search is due on Friday.
Even though we'll have a lab for it on Monday.
Oh, no. It's a week from Friday. You have 1 week off.
Okay.
That's how I did it. You have 1 week off. Because the second lab will,
On Monday. Next week.
you have a week off.
To
If
work hard.
Sushmita gives you, if she gives you points off or not, I'll try to remember to tell her
So
about
it's not
that.
due Friday?
Huh?
It's not due Friday? No.
It's going to be due a week from Friday. But get it in on Friday. I mean, really, do it. This is not hard, right? Well, actually, there's a lot of problems.
Alright.
There are a lot of problems. These are due next week. And then sorting is due the Friday after November 23rd. And then after this, we only have one more lab, right? And that's spread out, one more activity, one more exercise, and that's spread out over 2 weeks. Oh, the exam is on the 18th. When is that?
Week from Wednesday.
A week from Wednesday. Now the exam includes a problem on binary search. I'm asking you to show me that you know, that you have memorized the algorithm of binary search. I'm not going to tell you the form. Is it a vector? Is it an array? Is it ascending? Is it descending? Is it return true or false, or is it return the index? All of those variants of the problem are possible to appear on the exam. There will be one problem on the exam for that. I will not ask a problem on sorting. So if you can get binary search done by this Friday, it makes a lot of sense, right? Yeah, all right. So that's it.